Hi everybody, welcome back to my stats podcasts. Just find a lecture thing. There we go. So, a little bit about last week's task again. Here is some of the pictures and so on from the compendium. First thing to note is you should comment on the distribution of the data, which you can get from the box plots. Here are the names of the variables, and you should be familiar with the box plot layouts now, and you can get an impression of the distribution from these, whether or not the whiskers here are symmetrical and the placement of the median within the interquartile range box, this thing here. Okay, it gives you an impression of that, and also you can tell if there are outliers and so on. Of course, if you wanted to go beyond this, you've also learned in previous weeks that you could have done a QQ plot, okay, which we can see on the next page here. Here's some examples from of three of the variables, and as we can see, a lot of the data is pretty much along the normal line. However, again, at the extremes of the tails here, we're seeing what's called a floor effect. These participants have all been given the same value, just below 60, and this is a ceiling effect. They've all been given a value of about 120 or something like this. But in between, we can see that this again is borne out by relatively close approximation to a normal, except in the tails of the distribution, and so this might cause you a problem for using your parametric statistical approach. So one thing you might want to do to get better estimates of where some of the descriptives are, like the median of the data and the typical spread of the dispersion of the data, you might decide to trim the data. Okay, so have you trimmed the data? Have you checked with QQ plots and so on? Checked for outliers? So if there are lots of outliers, or it's not normally distributed, then we've got a case for trimming. So before you trim, you check how far apart the median and the mean might be, for example, because you get the means from the tables there, and the medians and so on. You get a table of descriptive datas. If they're far apart but but move close together once you're trimming, that's good evidence that the asymmetry, any asymmetry in the distribution, has been corrected by the trimming. Okay, and then you have to think about what the significance of this is, and it's to do with the fact that the outliers were very heavily influencing the values that you might have reported by the trim without the trimming. So how much has the mean value for the trimmed versus untrimmed data changed? If it's changed a lot, it suggests that the outlier is having a big effect on the mean value, and so that's a good reason to use the trimming. And you can also look at how the standard deviation changes. Remember, I was saying in the lecture last week that if you've got outliers or very broad tails to the distribution, then there's a tendency for the standard deviation to be inflated, and this makes judgments about differences between things in the presence of this variation much more difficult to do. But you can go too far, so and don't over trim the data. Okay, so you just need to get to the point where the data have been corrected to some extent by the trimming, by the removal of the outliers, and some correction of the distributional form, so that you've got a good impression of where the median truly lies. But of course you can trim to the point where you've only got 2 or 3 points left, and then you haven't got enough data in your sample to make accurate estimations. Now, adding the notches to the box plots is a really cool thing, because apart from just giving you some of the descriptives, it gives you information about the variability of the data, and as a consequence we can make comparisons between the descriptives, in this case the median value of the different samples. So these two panels are for the untrimmed and 10% trimmed notch boxes side by side, and we can compare pairs and how their notches overlap. Look at this. So this bar here, my little pointer's gone again, is positioned at the top shoulder of the notches on the reading level variable box plot here. And we can see that now, although it's the notch falls within the notch range of the math skill thing, it's way below the range of both the writing and the knowledge boxes. So in terms of the variables that these things are measuring, we can say, because these notches don't overlap, okay, that there are significant differences at the 5% level between the values of the medians in the cases of these two variables and in the cases of that variable and that variable. That's reading and the fourth variable, reading and knowledge. Okay. Matrix scatter plots. This gives you an impression of the degree of association between different variables. Okay, so each child has got 5 scores, one on each of these variables. The variable names are plotted along here, and then for each pair of variables we plot their individual scores like this. Okay, so this child has got a score on the reading scale that is near whatever that value is. Looks like it's about 80, and then on the math scale has a low score which is about 60. So that's that child there. We do that for all the children, and some of the variables are more closely associated than others. Like this one here, you see there's a very strong association between reading and the skills measure, whatever it's measuring, but there's not so much of a strong association, for instance, between maths ability and this knowledge measure. Okay, because this is not so strongly clustered along a line here as it should be if they were closely related. Okay, this is not like doing a QQ plot. Okay, the QQ plot is on a single sample, and it tells you about whether or not that sample is distributed in accordance with a normal distribution function. This is comparing individual scores on pairs of variables to tell you whether they're associated or not. They don't have to come out as straight lines. It could be any shaped line, really. It could be a curvy line, but if you don't get the points just scattered all over the place, if there's some organisation, then it shows there's a relationship between these two things. And of course, it says at the bottom, something interesting to do with 2 different years. Okay, so we've got data for years 7 and years 10. Well, how about looking at the relationship between pairs of the same variables across different years? So we might want to look at the reading scores and the math scores for year 7 and, in this case, year 10, and see if there's close correspondences, which we would expect between and across years.